In this lesson, we will be learning our final test used to test for convergence, and this test can be applied to show convergence of a whole wide variety of different kinds of series. So the first thing we're going to do is define two different kinds of convergence, absolute convergence and something called conditional convergence. So a series is called absolutely convergent if the series of its absolute values is convergent, and a series is called conditionally convergent if it is convergent but not absolutely convergent. So tell me whether these series are absolutely or conditionally convergent. So a series is absolutely convergent if you take the absolute value of the terms in the series and then that series converges. So first of all, this series that we're given, just as is, this series converges by the alternating series test. It'd be really easy to show that the limit as n goes to infinity of 1 over n squared is 0, and also that the bn plus 1 is less than bn. Those parts are pretty easy. And then also, the sum from n equals 1 to infinity of the absolute value, so of all the terms in this series, that will just be the same thing as the sum from n equals 1 to infinity of 1 over n squared. This thing converges as it's a p-series with p equal to 2. So since the series of absolute values converges, this series is absolutely convergent. Determine whether the following series are absolutely or conditionally convergent. So this series converges by the AST. Now the question is, does the sum of its absolute values converge? So the sum from n equals 1 to infinity of absolute value, negative 1 over n to the n. Well, negative 1 to the n absolute valued is just going to be 1. So we have the sum from n equals 1 to infinity of 1 over n, which diverges, since that is the harmonic series. Okay, so since the series converges, but some of its absolute values do not, this is a series that is called conditionally convergent. So what we would like to conclude is that if a series is absolutely convergent, then it is convergent. I.e., we want to be able to say, well, if I know that the sum of absolute value of a sub n's converges, that implies that the sum of the a sub n's also converges without the absolute values. And one reason we really need to know this is because so far the test that we know, so we have the integral test requires you have a positive function, so positive terms. The comparison test require positive terms. The alternating series test, well, you can have negative terms there, but they have to flip-flop, so they must alternate. What if you have a series whose terms don't alternate exactly? How would you show that that converged? And this is what you would use. So we're going to prove this using comparison. So first note that 0 is less than or equal to an plus the absolute value of an, which is at most twice the absolute value of a sub n. So first of all, since you know that your series an is absolutely convergent, the sum of absolute value of a sub n's converges, and thus so does the sum of twice the absolute values. And that means that by direct comparison, the sum of an plus absolute value of an also converges. And then we can express the sum of just the ANs without the absolute value as a difference of two convergent series, one of which is the sum of AN plus absolute value of AN minus the sum of absolute value of ANs. So thus this series is a difference of two convergent series and is therefore convergent. All right, let's use this idea to show these following series are convergent. So the reason you can't apply the alternating series test is that this term does not alternate. Sometimes it goes positive positive or positive negative negative. So it's because the examples that we had before had a sign of like n pi or n pi over 2. Okay, so here's how you prove this. You use comparison. So you prove the absolute values converge. So first note that the absolute value of sine n over n squared, that's less than or equal to 1 over n squared. And this tells you that the sum from n equals 1 to infinity of sine n over n squared converges by direct comparison. And so thus the series is absolutely convergent. And therefore also just convergent. So the idea is that it's harder to be absolutely convergent. So if you can show absolute convergence, that implies convergence. So absolute convergence implies regular convergence. That does not go the other way. Regular convergence does not imply absolute. An example of that would be the sum of -1 to the n over n. That converges by the AST, but it is not absolutely convergent. So a similar idea here. You just notice that the absolute value of sine of n over 2 to the n is less than or equal to 1 over 2 to the n. And as the sum from n equals 1 to infinity of 1 over 2 to the n is a convergent geometric series, with r equal to 1/2, this series is absolutely convergent. By direct comparison. So we have a few tests to prove that a series is absolutely convergent. They are called the ratio test and the root test. I'm going to start by going through a few examples of how these tests work, and then we're going to discuss why they're true. So a series will converge absolutely if the limit as n goes to infinity of the absolute value of the ratio of its n plus first term to the nth term is less than 1. The series will diverge if the limit of that ratio is greater than 1, and this test is inconclusive, meaning it could go either way. If that limit is equal to 1. Notice that here that this 1 is awfully similar to the test for whether or not a geometric series converged. A geometric series converged if the absolute value of r was less than 1, a lot like this ratio having a limit less than 1, and it diverged if the absolute value of r was bigger than or equal to 1. And it turns out that proving this test involves comparison with a geometric series. Okay, so the way you apply the ratio test is you define what an is, and then you find the limit as n goes to infinity of the absolute value of an plus 1 over an. So an plus 1 means you input n plus 1 for all of the n's. So it's 5 to the n plus 1 over n plus 1 factorial. Dividing by a sub n is the same as multiplying by its reciprocal, which is n factorial over 5 to the n. And then these should simplify down quite a lot. So 5 to the n plus 1 is 5 to the n times 5, n factorial. N plus 1 factorial is the same thing as n plus 1 times n factorial. And now a whole bunch of things cancel, and we're left with the limit as n goes to infinity of 5 over n plus 1. And since we're plugging in only positive integers, we know that n plus 1 is a positive number. Well, this limit is equal to 0, which is certainly less than 1. And according to the ratio test, this means that our series converges absolutely. So thus, the series converges absolutely. It turns out this actually also has some negative terms, so we'll see what the absolute value does to those. So we'll find the limit as n goes to infinity of the absolute value of an plus 1 over an. So first input n plus 1 for all the n's. To the n plus 1. Then divide by an, or multiply by the reciprocal of an. 2 to the n over negative 1 to the n squared. So the first thing is that if you absolute value these negative ones, they can just become positive ones. So they don't matter, just ignore them. We have 2 to the n times n plus 1 squared over 2 to the n times 2. And also, I can just, once I absolute value the negative ones, I can drop the absolute value bars because everything else is positive. Times n squared. And this is the same thing as the limit as n goes to infinity, 1/2 times n plus 1 over n, the quantity squared. Now you could expand this n plus 1 out in the numerator, but what you can also notice is that as n goes to infinity, this expression inside the stuff that's squared goes to 1. So this limit approaches 1/2. 1/2 is less than 1. So thus, this series converges absolutely. And as we're going to need to refer these tests by name, let's just add by the ratio test. If you work this limit out and the limit is bigger than 1, you can conclude that this series will diverge. If the limit is equal to 1, you either made a mistake or you need to try a different test because this test is inconclusive. Now, another rather similar test is something called the root test. So a series will converge absolutely if the nth root of its nth term is less than 1. It will diverge if the nth root of its nth term is bigger than 1, of course, as n goes to infinity. And this test is inconclusive if this limit is equal to 1. So the conclusions are pretty much the same as for the ratio test. It's just the thing that you limit is the nth root as opposed to the ratio. You want to apply this test when you typically have things in both the numerator and denominator raised to the n. Notice I could have also written this as the sum from n equals 1 to infinity e cubed over n all to the nth power. So we find the limit as n goes to infinity of the nth root of the absolute value of the nth term so all that to the nth power. Well, that nth root and nth power can cancel each other out, giving us the limit as n goes to infinity, absolute value e cubed over n. And that's a positive number, anywho. So the limit as n goes to infinity of e cubed over n is actually 0. And 0 is less than 1. And the conclusion is the same as the conclusion we drew from the ratio test. Thus, the series is actually absolutely convergent. Let's say by the root test. Right here you also see that you have a 5 to the n power. So we're going to apply the root test. Find the limit as n goes to infinity, nth root, absolute value, an. All right, when you take the nth root of something to the 5n power, you would just end up with that stuff to the 5th. And as n goes to infinity, the stuff inside the power that's raised to the 5th goes to 2. The absolute value of that, so the absolute value of negative 2 to the 5th is 32. I had some students in the past who have concluded that this limit is just equal to negative 32, which is not true because of these absolute value bars. So if you feel like it, this limit can move inside that absolute value, which moves then inside the 5th power. First you find the limit of the stuff inside the 5th power, take the 5th power, then absolute value. So that limit is 32, which is bigger than 1. Thus, this series diverges. All right, now let's actually prove why this tests work. So this does involve comparison to a geometric series. So the basic idea is we're going to compare with a geometric series. You're going to need to write a little small to make this fit here, but the first one, proving convergence, is the hardest. Okay, so we're going to assume that the limit as n goes to infinity of an plus 1 over an is equal to some number L that's less than 1. We want to show that this means the sum of the absolute value an's converges. Okay, so since that limit goes to some number L, so since the limit as n goes to infinity of this an plus 1 over an goes to L, eventually we can find a number R where L is less than R, which is less than 1. Okay, so find a number R that's a little bit bigger than RL, but is still less than 1. And eventually the absolute value of an plus 1 over an is going to be less than this R for all the n's past a certain point. So eventually, because these terms are going to this number L, they have to be less than this number, or they have to eventually get close. And what this means, so this means that the absolute value of an plus 1 is less than r times the absolute value of an. I just got that by multiplying by this for n bigger than or equal to some capital N. So what that means is a sub capital N plus 1 is less than r times a sub capital N. It means that a sub capital N plus 2 is less than r, absolute value, a sub capital N plus 1. And from the previous inequality, we know that this is less than r times r, absolute value, a sub capital N, which is r squared, absolute value, a sub n. And similarly, the absolute value of a sub n plus 3 will be less than r times the absolute value of a sub capital N plus 2, which we just showed is less than r times r squared, absolute value, a sub capital N, or r cubed, absolute value, a sub n. Okay, so look at this. We have r squared, r cubed. If I had n plus 4, we'd have r to the 4th. So what you have then is this series where you add up a sub capital N plus 1 plus absolute value a sub capital N plus 2, etc. That's less than or equal to r absolute value a sub n plus r squared absolute value a sub n plus r cubed absolute value a sub capital N plus etc. And that comes from the fact that this term is less than that term. This term is less than this term, see that, and etc. Okay, now this thing on the left, that is the same thing as the sum from n equals capital N plus 1 up to infinity of the absolute value of an's. That's less than or equal to the sum from n equals 1 to infinity. N equals 1 to infinity, absolute value of an times r to the n. Notice that this series is geometric with r less than 1 because we assumed that was true above, and thus convergent. And what that tells us, this fancy word, hence the sum from n equals capital N plus 1 to infinity of an's absolute values converges. It doesn't matter how many terms you leave off in the beginning, you can still add up a finite number of things. So therefore, the sum from n equals 1 to infinity of absolute value of an also converges, and that's what you wanted to show. So it turns out divergence relies on the same idea, as in it's very similar, and it's actually a little bit faster to prove. So for case 2, so we assume that the limit an plus 1 over an approaches some number L that is bigger than 1, or that it approaches infinity. So then we know that the absolute value of an plus 1 over an is bigger than 1 for all the n's past a certain point, or an plus 1 is bigger than the absolute value of a sub n, And as a result, the limit as n goes to infinity of these an terms can't be 0. So this diverges by the test for divergence. And then a small note about the third case, the inconclusive case. So if you just try, so limit n goes to infinity, ratio an plus 1 over an. If you try this with the sum from n equals 1 to infinity, 1 over n squared, which we know converges, and the sum from n equals 1 to infinity of 1 over n, which we know diverges, in both of those cases, the ratio test will give you that the limit is equal to 1. So if you get that the limit is equal to 1, it could go either way. Your series might converge, it might diverge. To show that it converges or diverges, you're going to have to pick a different test. All right, let's talk about some more series. So a typical time when you want to apply the ratio test, so as a hint, is that you have factorials. That's often the case when you use this one. And also, whenever you have negative terms and you don't want to do the AST. Okay, so we're going to apply the ratio test here. So find the limit as n goes to infinity, absolute value an plus 1 over an. So when you input n plus 1, you have negative 3 to the n plus 1. And when you input n plus 1, it goes in for that n. You have 2 parentheses n plus 1 factorial. Multiply by the reciprocal of an, which is 2n plus 1 factorial over negative 3 to the n. So personally, I know those absolute values are going to take care of the negative sign, so I just ignore them. I'm making this 3 to the n times 3, now 2n plus 1 factorial. In the denominator, this factorial becomes 2n plus 3 factorial times the 3 to the n. So the 3 to the n's obviously cancel. In the numerator we have 3 times this 2n plus 1 factorial. If I expand out that bottom one, the highest number is 2n plus 3. One down is 2n plus 2. One more down is 2n plus 1. So there you go, you get your 2n plus 1 factorial. So now those cancel, leaving us with the limit as n goes to infinity, 3 over 2n plus 3 times 2n plus 2. And that limit is equal to 0, which is less than 1. Thus, this series converges absolutely. It doesn't immediately seem obvious that this is the ratio test, but I think it would be a little bit more obvious if you'd write this as the sum from n equals 1 to infinity n over e to the n. The integral test might also work here, but if you're going to do that, you're going to have to use a derivative to prove the function's decreasing, and to do the integral, you probably actually have to do integration by parts. So we're going to bag that idea, and we're going to try the ratio test and hope we do not get an inconclusive result. All right, so inputting n plus 1, we end up with n plus 1 over e to the n plus 1 multiplied by e to the n over n. Now e to the n plus 1 is e to the n times e times n. So that's the same thing as the limit as n goes to infinity of n plus 1 over e times n, which it appears to be 1 over e. And since e is about 2.718, 1 over e is definitely less than 1. And as a result, this series converges absolutely. So now that you know both tests, it's your job to kind of determine when you should apply one or the other. The ratio test will work whenever the root test will work, but sometimes the root test will just be a lot faster. Notice here both the numerator and denominator are raised to the nth power. That's a hint to try the root test. So find the limit as n goes to infinity, nth root, absolute value a sub n. Let's just write that as the absolute value of negative 5 over n all to the nth power. So the nth power and the nth root cancel, and then we absolute value and just get 5 over n. And that limit is 0, which is less than 1. Thus, this series converges. Absolutely. Right here we have stuff raised to the nth power, but whenever you have a term that's not the root test is probably a bad idea. Nobody ever seems to be able to do it successfully. So if you have a term like that in there, give the ratio test a try. The trickiest thing with the ratio test is inputting n plus 1 correctly. When you input n plus 1, we get 10 to the n plus 1 in the numerator. In the denominator, n plus 1 makes n plus 2. And then 4 to the power of 2 times n plus 1 plus 1. Multiplied by n plus 1, 4 to the 2n plus 1, all over 10 to the n. All right, let's just simplify that down a little bit. So that becomes the limit as n goes to infinity. We have no negatives here, so I'm just going to drop the absolute values. We've got 10 to the n times 10, n plus 1, 4 to the 2n times 4. In the denominator, we have an n plus 2 factor, 4 to the 2n, and then also a 4 to the third, because this exponent down here is 2n plus 2 plus 1, or 2n plus 3. And then we have another 10 to the n. And a whole bunch load of stuff cancels. The 10 to the n cancels, the 4 to the 2n cancels. One of these 4s will cancel that out and make it a squared. So we have the limit as n goes to infinity of 10 times n plus 1 over 16 times n plus 2. And that limit will be 10/16, same thing as 5/8, reduce your fractions, which is less than 1. So thus, this series converges absolutely. Alright, this one, arctan of n. Oh, and to the nth power. Well, you could do the ratio test, but probably a much better idea to do the root test. find the limit as n goes to infinity of the nth root, absolute value an, so absolute value of arctan of n to the nth power. Well, those nth roots cancel out, and as we plug in positive n's, arctan's a positive function. And remember that as n goes to infinity, arctan n has a horizontal asymptote of pi halves. So this approaches pi halves. And that is bigger than 1, since pi is about equal to 3.14. Pi over 2 is about equal to 1.57, which is definitely bigger than 1. So thus, this series diverges. All right, here, the sum from n equals 2 to infinity, ln of n over n. Well, since I have this all to the nth power, I'm also going to apply the root test. So let's find the limit as n goes to infinity, nth root, absolute value, an. All right, the nth root and nth power cancel out. We only care about positive n's, we can drop the absolute values. And you want to conclude, or hopefully you can conclude, this limit is less than 1. We can't conclude anything yet. This is an infinity over infinity form for a limit. So we use L'Hopital's rule to determine what that limit equals. So this equals the limit as n goes to infinity. The derivative of ln of n is 1 over n. The derivative of n is 1. So that limit equals 0, which is less than 1. And as a result, so thus, this series converges absolutely. All right, here's a warning. If the ratio test or root test fails, which means you get that that limit is equal to 1, you must apply a different test to determine convergence or divergence of your series. So we are going to try to apply the ratio test to this expression, and I'm going to show you that you get the limit is 1, it's inconclusive, and discuss what your other options are if this happens. So find the limit as n goes to infinity, an plus 1 over an. So inputting n plus 1, we have negative 1 to the n plus 1, all over n plus 1 cubed plus 1, multiplied by n cubed plus 1 over negative 1 to the n. The negative 1s don't matter, they just get absolute valued and they go away. So we have n cubed plus 1 over, now to figure out n plus 1 cubed, that's n plus 1 times n plus 1 times n plus 1, which I worked out to be n cubed plus 3n squared plus 3n plus 1. Adding that to this additional one, we get n cubed plus 3n squared plus 3n plus 2. And this limit, you can multiply the numerator and denominator by 1 over n squared, n cubed, and you get that this is the limit as n goes to infinity of 1 plus 1 over n cubed over 1 plus 3 over n plus 3 over n squared plus 2 over n cubed, and that is equal to 1, which means crap, inconclusive. All that work for nothing. Very sad face. So you ask yourself, what are the other options that you could use? So what are the other tests that you know? Well, you know the integral test. Nope, can't use it here. Must be positive terms. You know the comparison tests, as in both the limit comparison and direct comparison. Once again, nope, you need positive terms. And your final option is the alternating series test, and you say, woohoo, I can apply that one. So we're going to apply the alternating series test. So first thing is let your b sub n be 1 over n cubed plus 1. For the alternating series test, you must show that the limit of the terms is 0. And as we only have a variable in the denominator, this is definitely 0. And then also, the n plus first term is less than the nth term, as 1 over n plus 1 cubed plus 1 is less than 1 over n cubed plus 1. If you increase the denominator, you decrease the size of the ratio. So this series converges by the alternating series test. So in general, the ratio test and root test will fail whenever you have a question that is something over a polynomial. So if you have other things with like exponentials mixed in with the polynomials, then it will probably work, but in this case, not so much. So once again, your options are integral test, the comparison test, and the AST. You see a -1 to the n, it's probably the alternating series test. So we're going to let b sub n be 1 over 5n plus 1. It's actually a pretty easy alternating series test. First, the limit as n goes to infinity of 1 over 5n plus 1. Well, that's definitely 0 because you only have a variable in the denominator. And also, the n plus first term is less than the nth term, as 1 over 5n plus 1 is less than 1 over 5n plus 1. Notice this first one really is 1 over 5n plus 6. And if you add 5 to the denominator, then the fraction definitely is getting smaller. And since both conditions are met, thus the series converges by the AST. All right, here, well, you probably could do the alternating series test, but since you see you've got 5 to the n, it appears that the ratio test will work. Ratio test works well when you have stuff to powers. You don't want to apply the root test because this n does not have an nth power. Only apply the root test if every single term is raised to the nth power. All right, find the limit of the ratio of the n plus first to the nth term. -1 to the n plus 1 times n plus 1 over 5 to the n plus 1 multiplied by 5 to the n over -1 to the n times n. Now those negative 1's can go away. We can cancel the 5 to the n's, and we're left with n plus 1 over 5n. And that limit will be 1/5, which is less than 1. So thus the series converges. Absolutely. By the, tell me what test? By the ratio test. All right, here, once again, if you attempt to apply the ratio test or a root test, they will not work. So once again, you've got a -1 to the n. Well, it seems like the alternating series test is a really good candidate. So let b sub n be 1 over ln of n. So first thing to note, that the limit as n goes to infinity of 1 over ln of n, well, as n goes to infinity, ln of n goes to infinity, and this is equal to 0. And then we need to show that bn plus 1 is less than bn. Well, you know that ln of n plus 1 is bigger than natural log of n because natural log of is an increasing function. It looks like this. So as the n's increase, the y values increase. So 1 over ln of n plus 1 is less than 1 over ln of n, which tells you b sub n plus 1 is less than b sub n. So thus the series converges by the AST. All right, here we see the whole ratio is raised to the nth power. That's a hint that you probably should apply the root test. So find the limit as n goes to infinity of the nth root of the absolute value of your nth term. Well, the nth root can cancel out that nth power. Absolute value 2 minus 3n over 1 plus n. Now technically this limit can go inside that absolute value because the absolute value is a continuous function, and the stuff inside the absolute value bars goes to -3. So you have that this limit is -3 absolute valued, which equals 3. As that's greater than 1, the series diverges. So thus the series diverges by the root test. All right, here we have a series that's defined a little bit differently. So we have the terms defined in a recursive manner. We know our first term is 2. Our subsequent terms are found by plugging stuff into this formula. I'll just find a sub 2 and show you what it is. The way you'd find a sub 2 is you'd plug 2 in for n. And then you would note that, well, this is 1 more than that. So if this is 2, this is 1, and a sub 1 is 2. So that is 810 over 11 times 2, or 20 over 11. So that would be a sub 2. You'd find a sub 3 using this 20 over 11 for the a sub n. So our question is, what's going to happen? So what happens to the series if we add all of these terms up? And it turns out that in this case, applying the ratio test will actually work quite nicely. So we're going to find the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And we were given that the a sub n plus first term is 4n plus 2 over 5n plus 1 times an, and an is just an. Notice how those an's cancel. We said the limit as n goes to infinity of 4n plus 2 over 5n plus 1. Well, that's just 4/5, which is less than 1. So thus, the series where you add all these things up, sum an, converges. by the ratio test.